This is ELC131, Circuit Analysis 1, and this video discusses the Wheatstone Bridge. Now, in your studies and your careers in electronics, electricity and electronics, you may encounter many different bridge circuits. The Wheatstone Bridge was originally designed to allow us to measure unknown resistances. And of course now primarily the Wheatstone Bridge is used in instrumentation. You may encounter the Kelvin bridge, you may encounter the Wein bridge, the Maxwell bridge, the H bridge, the Schering bridge, and or the Varley bridge. Now there are many more bridge configurations. However, they were simply too numerous to list in this presentation. Of all the bridge circuits, the Wheatstone Bridge is the one that you're most likely to encounter in your studies and your careers in electricity. The Wheatstone Bridge is now widely used in a branch of electronics called instrumentation. And instrumentation is simply the term we give to the branch of electronics involving performing or obtaining an electrical measurement of a physical parameter, such as temperature. Now, the circuit of Figure 1 shows us the basic configuration of a Wheatstone bridge. Resistors R1 and R2 comprise what is called one leg of the bridge. R3 and R4 make up the other leg of the bridge. And for this example, connected across the bridge is a galvanometer. And the galvanometer is simply an analog measuring device that allows us to measure current in either direction. Hopefully you remember seeing an application of the galvanometer in the Sources of Electricity video, where we connected a galvanometer to a coil and we're able to obtain current in one direction when I move the magnet in, and current in the other direction when I move the magnet out. Now, with our bridge circuits, one key term is when the bridge is balanced. And for the Wheatstone Bridge shown in Figure 1, we say the bridge is balanced when R1 over R2 equals R3 over R4. Now, this does not mean that R1 has to equal R3 and R2 has to equal R4. It simply means the ratio of R1 over R2 equals the ratio of R3 over R4. Now, the balance condition is important because when the bridge is balanced, there's no current through the galvanometer. And when there's no current, the voltage across the galvanometer is 0 volts. Now, let's look at an example of a balanced bridge circuit. Let's calculate the value of R4 required to balance the bridge circuit of Figure 2. So we start with our equation that describes a balance condition in this bridge. R1 over R2 equals R3 over R4. Rearrange the equation to solve for R4. Substitute the known values for R3, R2, and R1 and solve. So if in the circuit of Figure 2, if R4 has a value of 21.4 k ohms, the bridge will be balanced. Now, an unbalanced bridge simply means that R1 over R2 does not equal R3 over R4. So we look at the circuit of figure 3, and you can see that a balanced condition does not exist. And when the bridge is not balanced, current will flow through the galvanometer. And if you again refer to the circuit of figure 3, note that two currents flow through resistor R4. The current that flows through R3 and the current that flows through the galvanometer. Because two currents flow through resistor R4, I cannot reduce this circuit using the series parallel circuit reduction techniques that we have studied in the past. Therefore, an unbalanced Wheatstone bridge cannot be reduced and analyzed using our traditional series parallel circuit analysis techniques. However, if the bridge is balanced, we can analyze the circuit. If the bridge is balanced, the current through the galvanometer is 0 amps. Therefore, I can remove the galvanometer and I won't change anything. The current through an open is 0, and the current through the galvanometer with a balanced bridge was 0. So with the circuit of figure 4, removing the galvanometer will not change the current through the resistors R1, R2, R3, or R4. And the circuit of figure 4 can be analyzed because R1 is in series with R2, R3 is in series with R4. This circuit can be reduced and analyzed to find the branch currents and the voltage drop across each resistor. Now, if the bridge is balanced, the voltage across the galvanometer is 0 volts. If the voltage across something is 0, I can replace that something with a piece of wire and nothing changes. We assume the voltage across a piece of wire or a short is 0 volts. So if the bridge is balanced, as we see in figure 5, I can replace the galvanometer with a short and nothing changes. The voltage was 0 anyway. And the circuit of figure 5 can be analyzed with our traditional series parallel circuit analysis techniques, because R1 is in parallel with R3, R2 is in parallel with R4. So I can reduce the parallel combination of R1 and R3 into a single resistance. I can reduce the parallel resistance of R2 and R4 into a single resistance. I can find the currents and the voltages in this circuit. So we can analyze a circuit only if it is balanced. Now let's look at an application of the Wheatstone bridge. The circuit of figure 6 shows us a Wheatstone bridge with resistor R4 replaced with a negative temperature coefficient thermistor. And we talked about thermistors in a previous video about resistance. I've replaced the galvanometer with a load resistor and connected a voltmeter across that load resistor. Now, for this circuit application, R sub O, the thermistor resistance at 25 degrees Celsius, is 10 k ohms. Therefore, the bridge will be balanced at 25 degrees Celsius. The voltage across the load is 0 at 25 degrees Celsius. However, the voltage across the load resistor will go positive at temperatures above 25 degrees Celsius and the voltage across the load resistor will go negative at temperatures below 25 degrees Celsius. Because as hopefully you recall from our discussion of thermistors, this is a temperature-dependent resistance. So, Figure 7 shows us the resistance of that thermistor as a function of temperature. And you note that at 25 degrees Celsius, the At 25 degrees Celsius, the temperature of the thermistor is 10 K ohms. At temperatures below 25 degrees Celsius, the resistance increases. At temperatures above 25 degrees Celsius, the resistance decreases. Therefore, at resistances below or above 25 degrees Celsius, the bridge will be out of balance. So looking at Figure 8, we see that at 25 degrees Celsius, the voltage across the bridge is 0 volts. That's because at 25 degrees Celsius, a balance condition exists. At temperatures below 25 degrees Celsius, the voltage across the bridge is negative. At temperatures above 25 degrees Celsius, the voltage across the bridge goes positive. Now, if you look at the graph of Figure 8, notice that from 0 degrees Celsius to somewhere around 50 degrees Celsius, the response of the bridge circuit, or the voltage across the bridge circuit, is fairly linear, even though there's a very nonlinear response in the thermistor voltage, or the thermistor resistance, from 0 to 50 degrees. This is one of the reasons we utilize the Wheatstone Bridge in an application like this, because we're able to obtain a fairly linear output voltage, or voltage across the bridge, even when we use a very nonlinear device such as the thermistor. So there are many different configurations of bridge circuits. However, the one that you are most likely to encounter is the Wheatstone Bridge. It's widely used in instrumentation to obtain a voltage due to a change in a physical parameter such as temperature.